All righty, let us go ahead and get started. So today we are going to continue talking about circuits, kind of a basic circuit analysis. Specifically talking about what happens when we have multiple resistors in a circuit and we have to combine them to be able to analyze what's the total current or things like this. What we saw in the previous lecture was that for our purposes, circuits can have resistors that are either connected in what's called series or parallel. And of course, you can have multiple of these in the same circuit. You could have some resistors that are connected in series, and then that set of series resistors can be in parallel with something else, and so on. But overall, the resistors will be in some combination of series connections and parallel connections. And we know how to combine those resistors depending on how they're connected. And so what we found was that the total resistance in series is just given by the sum of all the resistors that are connected in series. So if you have multiple resistors, they're all connected in series. You want to know the total resistance of that set. You just add up all the resistors together to get a total resistance. Parallel is the one that's a little strange. If you have multiple resistors connected in parallel, and you want to know what's the total resistance of that set of resistors, well, you don't just add the resistors, but rather what you do is you add the reciprocals of the resistances. And so it goes like this: 1 divided by the total resistance in parallel is given by 1 divided by R1 plus 1 divided by R2, and so on. And what's important about this one is, first of all, of course, you're not just adding the resistances, you have to add the inverses or the reciprocals. But then also, once you've done that and you have an answer, that answer is 1 over the resistance. So you have to take another step and flip that answer upside down, or take the reciprocal of the answer. And so you can't forget that step, because obviously you'd have a wrong answer if you did. And so what we want to do is do some examples. Make sure that when we look at a circuit and we see how the resistors are connected, we're able to analyze it in such a way as to simplify it down to the nice basic single resistor type circuit. So here's an example. Let's say we have this circuit. Okay, has 10 volt power source. Let's say this is 1 ohm and this is 2 ohms. And the question is, what's the total resistance of this circuit? Well, what you do is, when you are given a circuit, is you look at the resistors and you try to figure out what connections are series connections, what connections are parallel connections. So when I look at this circuit, I say, okay, if they're in series, what I would see is the current coming into a resistor would then have to inevitably go through the other resistor. So looking at this guy here, we have the current leaving the power source. It travels through, hits resistor 1 and goes through, but then continues on, and then has to go through resistor 2. There's no way for the current to avoid resistor 2 if it goes through resistor 1. Another way of visualizing it would be something like this. You have a pipe and you're allowing water to flow through the pipe, and then all of a sudden you get to a point where there's a constriction. Okay. Well, notice the water has no choice but to flow through this constriction. Even if I were to have drawn the pipe a little differently, where it goes down like this, then it constricts. Well, the same thing. The water's flowing here, and it's inevitably going to have to get through this constriction. That means this is series. The current has no choice. If it goes through one, it will go through two as well. And if you see something like that, that tells you, okay, this connection is in series. And if it's in series, then we say the total resistance in series is given by the first resistor plus the second plus however many there are that are connected in this way. In this case, it's 1 plus 2, which is 3 ohms. Okay, so fairly basic example. You have a couple of resistors. Don't let the drawing fool you by seeing the fact that the resistors look like they're drawn parallel to each other in terms of their geometry. Don't look at that, but rather look at what happens to the current. What are the electrons going to do? As they're flowing through the wires and they hit this first resistor and they come out of it, can they avoid the second resistor? If so, then they're kind of in parallel with each other. If they can't avoid each other, then they must be in series. Okay. Another way, as I said last time, is through looking at nodes. It's kind of imaginary concept. And the concept goes like this. For every element, every piece in your circuit, you put a node, and a node is just like a dot on each end of that element. And so look at the resistor 1, I'll put a node over here for his left side and a node over here for his right side. And of course for resistor 2, a node on his left side, a node on his right side. And we have the voltage source, a node on his top and a node on his bottom. And now we have a node on every side of every element. Then we look at the right side over there. If you notice, there's just a wire connecting these two nodes together. There's nothing branching out to another path. There's not another element sitting there. It's just a piece of wire. And because of that, what actually happens is these two nodes become one single, like a super node. Okay, even though it looks like it's two, because there's nothing but wire connecting them, they're actually one thing. And now we use the rules. Now we say if two resistors share only one node in common, then they're in series. Whereas if they share both nodes in common, that is both sides, then they would be in parallel. And so we look at this example and we say, okay, resistor 1 and resistor 2 share the node on the right, but notice the nodes on the left are different nodes. They don't touch each other. On the left of 1 is not touching resistor 2. And same goes for the one that's on the left of resistor 2. And so they only share one node in common. Since they share one node in common, they're in series. Once I know they're in series, that's when I use a little equation to figure out the total resistance of that connection. All right, so any questions about that particular example? All right, well, that's a little too simple. Let's go with something a little more complex looking. What if we had something that looks like this? Okay, 10 volts, 2, 4, and 6. Here we have a circuit with 3 resistors in it, and I'd like to find the total resistance of this particular circuit. So I have the same kind of thing going on. I have to figure out if these resistors, how are they connected? Are they series? Are they parallel? Are they a combination of the two? And so I look at what's happening here and I see, all right, if I look at the current's going to flow, it's going to flow, and then all of a sudden it hits this point right here. And at that point, the current can diverge. It can either take the path downwards towards resistor 2, or it could take the path to the right. Well, that's a clear sign that we have some kind of a parallel connection here. Because remember, the rule for series is the current has no choice. If it hits this resistor, it must hit the next one. Here, if it hits resistor 2, then it's going to avoid resistor 4 because it's just going to go back around the circuit without ever going to the right side. And likewise, if it skips over the 2 and goes to the 4, well, then it's going to skip the 2 and not touch it. So here we have these two resistors. If the current hits one of them, it won't hit the other, and vice versa. So you would say those two must be in parallel. But we could use the same argument to talk about resistor 6. If the current goes to 2, then it's going to avoid 4 and it's going to avoid 6. If it goes to 4, it's going to avoid 2 and it's going to avoid 6. And then, of course, if it goes to 6, then it's going to avoid 2 and 4. So in this case, not only do we have 2 resistors in parallel, we actually have 3. All 3 of these resistors are in parallel. Now, what's the other way of seeing it with the node method? Well, with the node method, I do the same thing I did before. Every element gets a node on either side. So here's the ones for 2, here are the ones for 4, here's the ones for 6. Well, notice at the top, those 3 nodes, there's nothing in between them except for wire. So really, all 3 of these nodes are just one big node. And the same goes for the bottom. In fact, if I wanted to, I could think of this circuit as looking something like this. These two circuits are the same circuit. Where here, this node here is like the top node, and the node over here on the right is like the bottom node. They're all coming from a single point. And a circuit diagram way of drawing it, you would draw the top way because it's clear to someone looking. The bottom way is a little messy, but visually it's easy to see that all 3 of those nodes are really the same thing, the same point. Okay, and so what happens is you get into, if you're going to be a circuit designer or analyzer or anything like that, you start to get used to, you get a feel for how these circuits are based on the circuit diagram. The circuit diagram, it's not perfectly clear that those 3 nodes at the top are all the same node because they look like they're different points in the circuit. And that's why we have to use the rule that if there's 3 nodes or 2 nodes sitting there and nothing in between them but wire, they really are the same point. The electricity doesn't see it as 2 different points. So anyway, now I know they're in parallel. Once I know that, I just use the equation. 1 over the total parallel resistance is 1 over R1 plus 1 over R2 plus 1 over R3. So 1 over 2 plus 1 over 4 plus 1 over 6. Say, okay, I need to add these. Let's say I don't have my calculator on me. In order to add fractions, you have to get a common denominator. In this case, the common denominator would be 12. And so this is the same as 6 over 12 plus 3 over 12 plus 2 over 12, which is 11 over 12. However, that's not my answer. That's 1 over the answer. So the actual answer is just a reciprocal, which is 12 over 11. And of course, if you had a calculator, you just get a decimal answer. That's perfectly fine. But I don't have my calculator with me, so I'll leave it as a fraction. So any questions about this example? All right, again, kind of basic. There's only one connection here. It's parallel. There's not a combination. So what about if we have a combination connection? Let's look at that kind of an example. Let's say we have something like this. All right, so this is 2, 4, 3, 8, 10. There's our circuit. And for this circuit, we want to know what's the total resistance flowing, what's the total resistance of this circuit. So same process. I want to try to whittle it down to a final total resistance. Now here it's a little more complex because I can tell I've got kind of a combination of things going on. Not everything is series, not everything is parallel. There's little bits and pieces. So I just do it one at a time. I go one step at a time, simplify one part. Once it's simplified, look at the circuit again with the simplification, and then simplify it some more. So when I look at this, I say, okay, this top piece up here, there's some parallel connection here, right? You've got this right here, that point, there's a divergence where the current can either go through the bottom path or the top path, okay? So that tells me the top path and the bottom path are parallel to each other. However, the bottom path is complex itself. There's actually a series connection sitting there. The 2 and the 4 share this one node in the middle there between them in common. So what do? I've got plenty of options here. The first option is to say, I know the 3 is in parallel with the 2 and the 4. So can I just do 1/3 plus 1/2 plus 1/4 to get that parallel piece? And the answer is no, you cannot do that. How do I know I can't do that? Well, if I could, what that would mean is that all 3 of these resistors are parallel to each other. Just like in the previous example, I had 3 resistors. The 2 is parallel to the 4, and the 2 is parallel to the 6. And the 4 is parallel to the 6, and the 4 is parallel to the 2, and so on. All 3 are parallel to each other. Here, the 3 is not parallel to the 2, and it's not parallel to the 4, but rather what it's parallel to is this combination of the 2 and the 4. And of course, it's also obvious that the 2 is not parallel to the 4 at all. It's actually in series. So I can't use that first try, that first attempt. Another thing I can't do is say, well, what about the 1 and the 3, 1/3 plus 1/2, and get this piece of parallel, and then do the 1/3 plus the 1/4 separately and get that piece of parallel. And then I add these two things together. No, bad. Can't do that either. Because again, the 3 is not strictly parallel to the 2. If I ignore the 4, notice that the 3 and the 2 don't share both of their nodes. The 3 has the yellow nodes. The 2 has the green nodes. Well, they share the node on the left, but the nodes on the right are not the same nodes. They don't share 2 nodes in common. They cannot be in parallel. And certainly they're not in series, because if they were in series, then if a piece of current hit the 2, it would also have to hit the 3. But we could see logically that once the current gets to that yellow node on the left, it must choose a path. It must either go to the 3 or go down to the 2. So it can't be in series either. So I'm left with a conundrum. What do? Well, the rule is usually if you have something that's complicated looking, but within that complication are some simple pieces, work on the simple pieces first and see what happens. And so what I would do is I would look at the 2 and the 4. I know the 2 and the 4 are in series. I can look at it and tell that. And so what I would do first is I would add in series the 2 and the 4 to get 6. And now I would redraw the circuit to see what it looks like. This bottom path is now a single resistor whose resistance is 6, and the top path is still sitting there. I didn't mess with him. So that's a 6, this is still a 3, and this is still an 8. Now I look and I say, okay, this is a little better because I can see that the 3 and the 6 share these 2 nodes in common. They're parallel to each other. Notice they're not parallel to the 8. Although it looks like it could be all 3 of these things in parallel. If we look back at our first example, I saw that these 2 things are not parallel. They're actually in series. They only share the 1 node. In fact, if an electron hits the first one, it must hit the second. Well, if I look at this, same kind of a thing happens. Yes, when it hits this first node on the left, it splits and either hits the 3 or the 6. Let's say it hits the 3. So whoop, here it comes, hits the 3. Comes down, then what's going to happen? Well, then it's going to come along and it must hit the 8. So somehow the electron cannot avoid the 8 if it goes to the 3 path, and the same holds for the 6 path. If it goes to the 6, it also must hit the 8. Remember, parallel would say if it hits the 3, it can avoid the 8 if they're in parallel with each other. It must avoid the 8, actually. But here we see that if it hits the 3, it will hit the 8 too. So what this is telling me is the 8 is in series with this stuff somehow, but it's not strictly in series with the 3 because the electron can avoid the 3. It could go to the 6 instead. It could hit the 6 and then go to the 8. And of course, it can avoid the 6. It could go to the 3 and then the 8 and avoid the 6. So the 8 is not in series with the 6, nor is it in parallel with, nor is it in series with the 3. However, whatever's happening with the 3 and the 6 there, whatever the electron does, once it leaves that part, it will hit the 8. So in my mind, what I'm thinking in terms of the reasoning is that I call this set of things up here the parallel set. Well, that parallel set is what's in series with the 8. Because the electron will hit the parallel set, do something there, and come out of it and definitely hit the 8. So the 8 is in series with this set of things. But the set of things itself is already complicated. So let me work on that complication first. Look at the 3 and the 6. The 3 and the 6 are definitely parallel. So 1 over r parallel is 1 over 3 plus 1 over 6. Well, 1 over 3 plus 1 over 6 at 3 over 6. But again, that's not r parallel. That's 1 over r parallel. So r parallel is 6 over 3, which is 2. And now I could redraw the circuit, and instead of having this parallel set of things, I could replace it with just one thing. Here it is. And his resistance is whatever I just calculated to be, which is 2. And now we can see we're back to the very first example we did today. I have the resistor 2 at the top, the resistor 8 at the bottom. The current flowing, if it flows through the first resistor, it will flow through the second, so they must be in series. So this is what the 8 is in series with. It's not in series with the 3. It's not in series with the 6. What it's in series with is this parallel combination of 3 and 6. And so that's what I work on. I now say, okay, total resistance in series is the 2 plus the 8, which is 10. And once I've done that, I'm left with a single resistor whose resistance is 10. So that's the total resistance. And there we go. That's how you analyze a circuit like this. I started with something fairly complicated. I've got 4 resistors sitting here. Some of them are in series, some of them are parallel. What do? I go one step at a time. I see this complicated system and I know straight ahead the 2 and the 4 are series. So I work on them first. By the way, one other thing I've seen in the past, so I want to go ahead and mention it so you can avoid it, is what about the 8 from the very beginning? The 8 in series with the 4. Okay, they only share that right node in common, that right yellow node sitting there. They share one node in common, and the rule says that if they share one node in common, they must be in series. So can't I at this point say, oh, let me do an R series of 4 plus 8 is equal to 12? Well, again, the answer is no. How do I know the answer? I can't do that. It seems to follow the rule. Why the heck are you telling me I can't do it? The reason is clear. Look at what an electron would do. If the 4 and the 8 were in series, then it's inevitable that if the electron hits the 4, it must hit the 8, and vice versa. If it hits the 8, it had to have hit the 4 as well. That's what series implies. If you look at our first example, I usually say once the electron hits the 1, because that's the first one, it must then hit the 2. And thus they're in series. But the rule actually goes further than that. It also says the opposite. If it hits the 2, or the inverse, if it hits the 2, it must have hit the 1. It couldn't have gotten to the 2 without first hitting the 1. So when I look at this and I say, okay, well, if it hits the 4, it will hit the 8. That is true. But what is not true is that if the electron hits the 8, it must have also hit the 4. That's not true, because you can have an electron go up to the 3 path instead and get to the 8, and it avoids the 4. So since there's a way for an electron to hit the 8 without hitting the 4, the 8 and the 4 cannot be in series. And of course, the same goes for the 3 and the 8. Yeah, it's possible for an electron to hit the 3 and then hit the 8, but it's not necessary. It could go to the bottom path. It could hit the 2 and then the 4 and then the 8 and avoid the 3. So that's how I know I can't do like an intermediate series sitting there. Add the 8 to the 4 or something like that. The only thing I have sitting in front of me I can do, the only thing I know for sure is that an electron, if it hits the 2, it must hit the 4. And if it hit the 4, it had to have hit the 2 as well. There's no other way. So I know immediately the 2 and the 4 are definitely in series. Let me mess with that and see what I get afterwards. Maybe after I do that, the circuit will look a little easier and there's going to be something else I can see that will happen. And that's what happens here. I combine the 2 and the 4, becomes 6. And now I'm left with this top circuit here. And now I see a definite parallel connection. The 3 and the 6 have to be in parallel. So then I combine them together. That gives me some other circuit, a little more simple. And I see there's a definite series sitting here, and so forth. I can't give you any kind of recipe. I can't give you any kind of rule that says, given a circuit, do these exact steps and you'll always get your answer. I wish I could. But if I could, then electrical engineers would not be paid the big bucks because everybody could do it. The reason not everybody can be an electrical engineer is because it's not perfectly straightforward. Sometimes it takes some creativity and some tinkering to figure out what to do. So any questions on this particular example? All right, let's try another one. Let's see. How about this? All right, so what do we have? 2, 4, 3, 6, 8. All right, there's a circuit. Again, what do I want to do? I want to calculate the total resistance of this circuit. Well, when I look at this, there's 2 paths I could take. Okay. One path takes a little bit more being comfortable with this material. And the other path is the path I'm going to take because it's more for those people who don't have a lot of experience with this. Let's follow the same kind of rule I talked about in the last example. Look at what you know for sure is definitely true. Do that simplification and then redraw the circuit and see where it leads. But when I look at this, I can see in my mind the 2 is in series with this bulk thing sitting there. Okay. But it's not in series with the 3 by itself. It's not in series with the 6 by itself or anything like that. The 2 is in series with this thing. So that thing I'm going to have to simplify eventually. Well, let's look at the thing then. What do I see about it? Well, there's obviously something parallel going on. Because at this point right here, the electrons, the current, can diverge to either go to the top path or the bottom path. So there's something parallel about it. But before I can do the parallel part, the 3 is not in parallel with the 6. The 3 is not in parallel with the 8. What the 3 is in parallel with is the top branch. And the top branch is made up of multiple things. So let's look at the top branch. The top branch has 2 resistors. What do I know about them? They're connected in series, right? If an electron hits the 6, it must hit the 8. There's no avoiding it. Likewise, if it hits the 8, it had to have come from the 6. So because of that, the rule tells me, okay, the 6 and the 8 are in series. So let's add them. Our series is 6 plus 8, which is 14. Now what do? Just redraw this. It's the easiest way. Make sure our mind doesn't get confused. Everything I have in touch, I leave the same. This is still 2, this is still 3, this is still 4. And now this top branch, I've combined those 2 resistors together to get a single resistor whose resistance is this number 14 I just calculated. All right. Now what? Well, what can I do here? Again, the 2 is in series with this thing, but the thing is not yet simplified all the way down. So I look at the thing again, and what do I see? I see in this set, the 3 and the 14 are in parallel with each other. How do I know? Well, current hits this node sitting here, and it'll either go to the 3 or it'll go to the 14. And each branch just has the 1 resistor, right? There's no complicated bit of stuff on each branch. It's just 1 resistor on one branch, 1 resistor on the other. Thus, they're in parallel. So I could do the parallel thing. I say, okay, 1 over R parallel is 1 over 3 plus 1 over 14. All right, so get a common denominator. Let's see, 3 times 14 is 42. So the common denominator is 42. So it's 14 plus 3 is 17. But that's 1 over R parallel. So R parallel itself is 42 over 17. some number. Again, if you're using a calculator, this will be a decimal. All right, 42 over 17. Now what? Redraw the circuit again since you've simplified it. Here's my first resistor. Now this parallel set becomes one single resistor. There it is. And what do I know about it? Well, this parallel set has a total resistance of 42 over 17. So there it is. And everything else is the same as it was before. All right, now I look at this guy. So what do I know? Well, it seems to me that these three resistors must be in series. Because notice if the current's coming in, it's going to hit the 2. It has no choice. It has to hit the 2. From there, it has to hit the next one. And then it has to hit the third one. There's no paths that diverge. The electrons can't skip one of these. The electron will hit all three. Because of that, they must be in series. So I add them in series. Our series is 2 plus 4 plus 42 over 17. All right, so what is that? Again, I have to get common denominators here. So this is 34 over 17 plus 40, 50, 68 over 17 plus 42 over 17. Okay, 110, 144. 144 over 17. And let's see, can I simplify that down? I don't think so. So there we go. Now, of course, if I had my calculator, again, I would have, what would it be? Something like 8, 8.5, something like that. But there's my number. Fractions are fine. And so there's my total resistance. I've now combined all the resistors together, one step at a time, little by little, simplifying it down further and further until I can combine all of them together into one single resistor whose total resistance is whatever this number is. So, any questions about this example? Again, a fairly complicated looking circuit to begin with, multiple pieces. But if I just go one step at a time, little by little, each step is really not that bad. Now, granted, it's really easy watching me do it because I already know the steps. I'm looking at it, I know what to do. If I don't know what to do, if I'm very new with this and I'm uncomfortable with it, then it's not this straightforward because I have to try to figure out, how do I know if this is in series? How do I know what I'm allowed to add and what I'm not allowed to add? And my only advice on that is you have to practice a lot of these examples. The more of these you practice, the more comfortable you're going to get because you're going to see a bunch of variety. And you're going to keep coming across ones you haven't done before. And that'll teach you something. That way, when you get another circuit that's kind of similar to that thing, you've already been through that one. So that helps you with this one. But at the end of the day, you look at your circuit and say, which are the ones I know I can simplify for sure? In this case, the 6 and the 8 being in series, that's easy. Is the 2 in series with the 3? That's a complicated question. Let me leave it alone for now. What about the 4? Is the 4 in series with the 2? Well, the answer is actually yes. So I could have combined the 2 and the 4 at the beginning. However, the fact that the 4 is on the other side of this parallel guy, that makes it kind of complicated and kind of messy. So I don't want to mess with that. Let me leave it alone until the end. What do I know? What's the easy mode way of doing it? 6 and 8 are in series, combine them in series. See what's left over. That leaves a parallel set. A 14 and a 3 are in parallel. Combine the parallel, forget everything else. What do I get? Now I'm left with a circuit with 3 resistors, but they're all in series. Okay, combine them all in series. I'm now finished. Each step very easy, either series or parallel. And I'm always choosing to do the simplest thing I see in the circuit. All right, so any questions on adding resistors together, combining resistors? All right, well, here's the future. First of all, on Canvas, I posted a set of practice problems on this for resistors. Basically a bunch of examples, 10 examples or something like that. And I've posted the solutions as well. So work on them, practice them, try to do it without looking at the solutions. Also, the homework. I put a homework problem up with a circuit or two, I forget, one or two circuits that are just like this, calculate the total resistance type thing. So that homework is posted on Canvas. So start looking at that as well. You now have all the information you need to do that homework. Okay, you actually had it last class. What we're going to do next time is, now that we know how to combine resistors in these kind of complex circuits, let's actually answer the types of questions we want to answer. For instance, Ohm's law. Given a complex circuit like this, what is the current which would flow through this circuit? Or what's the power flowing through the circuit? Things like this. So it's not much of an advancement. We already know Ohm's law, V equals IR. If I know the voltage given in the problem, I want to find the current. All I need to know is what's the resistance. Well, that's what we did here. Take the circuit, calculate the total resistance. You now have the resistance. Now I know the resistance, I know the voltage. How do I get the current? I is V over R. Very easy. How do I get the power? Power is I times V. We saw that at the beginning of this subject. But we saw it, of course, with very simple circuits. Now we have more complicated circuits, so we have an extra step, and that step is calculating the total resistance. Once we're done, we would be done with electricity. And so we could have our first test. So it's looking like, okay, next class, which would be Tuesday, we would do the Ohm's law, finish up circuits. That Thursday, we would have an exam review. And then the following class period, the following Tuesday, would be our test. Okay. So that's kind of the time frame we're looking at. We're going to finish up circuits next time. Then we'll have a test review, see what topics will be on this test, what kind of the format of the test and all that kind of stuff. And then we'll have the test, and it'll be online. And like I said, the way the test is formatted, the way it's handled is just like the way the homeworks are handled. They're posted to Canvas as a PDF file. You download it, you work out the problems on a piece of paper or that piece of paper, showing your work, boxing your answers, and then you'd submit it back to Canvas. And I'd give you the full day to work on the test. So it won't be during the class time. It won't be a timed event where you have to be on Canvas and there's a little timer that says an hour and 15 minutes. I'll just post it and give you till midnight that night for you to submit it back. But again, we'll get more into the details of the test with the test review day. But I just wanted to kind of foreshadow what's going on. So we're almost done this topic. We pretty much have everything set, and we're just going to do finish it up. So if there are no questions, of course, you're free to go and enjoy your weekend eventually. If you do have questions, of course, you're free to ask, but if not, I will see you next time.